All right, welcome back. So, having studied trig integrals recently, we're now stepping up to study trig substitution. Ultimately, we're going to be looking at integrals which have square roots of degree 2 polynomials inside. And if you remember from what we saw in the video on trig integrals, this relates to the question that was studied by the mathematicians in the late 1600s about planets orbiting stars in ellipses and the areas that they sweep relating to the time that it takes for them to go around the star. And so if you take the expression for the equation for an ellipse and you solve for y, you ultimately get the square root of a degree 2 polynomial. So here is historical context as to why we ought to study these things. Before we get into the actual forms of trig substitution integrals, let me just make a note about square roots, right? Square roots do not work like this equation would suggest. Square roots are a multiplicative property, not an additive property. So when you have an addition sign inside a square root, unfortunately, that is problematic to simplification. So if you think that the square root of 3 squared plus 4 squared is 3 plus 4, take a moment to compute both sides. Here you'd have square root of 25, and here you have 7. Square root of 25 is not 7 as far as I'm concerned, and hopefully you agree that that's not the case as well. So the big thing, again, is the addition sign in between. Square root is not additive. Square root is multiplicative. And so actually, each of the 3 conventional forms of a trig subintegral has an additive, or I suppose a subtractive, but subtraction is just addition with a negative number, an additive or subtractive expression inside a square root. And this is problematic to simplification because simplifying square roots needs multiplication, not addition or subtraction. But how we sort of tiptoe around the algebraic complexity of simplifying a subtraction or addition sign under a square root in the case of having a degree 2 polynomial under a square root is utilizing trigonometry. So ultimately, in the case where we have a squared minus x squared under our square root, we're going to replace x with a sine theta, and that will have advantageous consequences. We'll look at that in a moment. If you get x squared minus a squared, which these are not the same thing, right? I mean, 5 minus 2 is different from 2 minus 5, right? So if you have x squared minus a squared, plug in x equals a secant theta, and good things will happen whenever you look at the trigonometric consequences. And if you have x squared plus a squared, plug in x equals a tan theta. So I mentioned that beneficial consequences occur as a result of the trigonometry. Let's take a look at this. So let's take the a squared plus x squared and plug in x equals a sine theta. So if you plug in x equals a sine theta, you'll get a squared sine squared for this bit of the expression. I've got that written out here. So we've got a squared minus a squared sine squared. Well, check it out. There's an a squared in both of those, so you can factor out. And what you'll be left with is just 1 minus sine squared. But 1 minus sine squared is exactly cosine squared by one of our trig identities. So how convenient is that? We just got rid of the subtraction sign under the square root, which is a huge win for our simplification. Now that we only have multiplication under the square root of a squared cosine squared would just be a cosine. So a nice benefit here for sure to utilizing trigonometry. The trigonometry replaces the subtraction sign with no subtraction sign, and hey, that's good for simplifying square roots. What about in the case where we had the x equals a secant theta? Imagine x equals a secant theta being plugged in here. You have a squared secant squared minus a squared, which is exactly what we've got written over here to the right. So then you've got a squareds in both of these terms. Factor out the a squareds, and then you just have secant squared minus 1. But hey, trig to our benefit, secant squared minus 1 is exactly tan squared. We have now gotten rid of the subtraction sign inside the square root, and what times itself is a squared tan squared, but a tan theta. So a nice simplification. Note the square root has wiped away in both of the first 2 cases, and in fact the square root will wipe away in this 3rd case as well. So we let x equals a tan theta when we have x squared plus a squared under a square root. The x squared, if x was equal to a tan theta, would be a squared tan squared. So that's where we start here. We've got a squared tan squared plus a squared. You can factor out the a squared, and you'll just get tan squared plus 1, which is precisely a trig identity. So you'll end up with a squared secant squared under the square root. the addition sign is gone from the square root, which is great for business when it comes to simplifying a square root. And then ultimately, what the a squared secant squared, what times itself is a squared secant squared, but a secant theta. And so this shows the benefit of utilizing trigonometry whenever you have square roots of degree 2 polynomials hanging out within your functions. And in some sense, it's not surprising that trigonometry comes into play because functions of the form square root of degree 2 polynomial relate to ellipses, and ellipses are related to circles. And so that all sort of feels right from a conceptual point of view. So I'm going to pause the video, scrub the slate clean, throw up one example. These are longer examples to work, I admit, but we'll work through one here today. You'll definitely work through more in class and through homework, fear not. And yeah, then that'll polish off our video for today, and that'll get us off and running with trig sub. Give me 1 second. All right, welcome back. Let's hammer through an example. And right, so one thing I've erased a bunch of stuff over here. One thing that I've added to the other side of the board is just to remind ourselves of something related to trigonometry. SOHCAHTOA is an acronym. Sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. This is when looking in a right triangle. I'll draw ourselves a right triangle here where we've got an angle theta. The side opposite is well opposite the angle theta. The hypotenuse is the big one opposite the 90-degree angle, and then the adjacent side is the side that's not the hypotenuse that's next to our angle theta. So here is our sort of picture of a right triangle. Why this will be necessary will manifest as we work through this example. So this example, integral 1 over x squared square root x squared minus 16 dx. Of all the things going on within this integral, the key object to focus on is that we've got a square root with a degree 2 polynomial inside. It would be lovely if this simplified to x minus 4, but it does not, because square roots do not simplify nicely with addition or subtraction. Square roots only simplify nicely with multiplication. And so, well, we've got to do something to simplify this out, but fortunately we have something available. So this is a conventional form of a trig subintegral of type 2, where you have x squared minus a squared, and we're going to use the substitution x equals a secant theta. Note, what would the a be here? Well, if we have x squared minus a squared, here the a that squares to be 16 would be 4. So just to make a couple notes here, here the a is equal to 4, and so here we have x equals 4 secant theta. That is what we're going to use as a substitution. Now, if x equals 4 secant theta, then dx is equal to, 4 secant theta tangent theta d theta. Excuse me. And now, plugging in the x and the dx accordingly, we can apply substitution to rewrite our original integral. So we'll have 1 over, now it's going to get pretty long here, but x squared is going to be 16 secant squared. Our square root is going to be x squared, well, that's also 16 secant squared, but then minus the 16. Now we know, and we have confidence that's going to simplify nicely. We've seen the general case previously. And then the dx is 4 secant theta tangent theta d theta. And it's about at this moment when you see this gigantic expression that you think, what in the world have we done? This is making things worse than they were originally. But you got to sort of have a trusting nature whenever it comes to trig sub, because we're going to work through this and you'll see it simplifies very nicely. Now, what about that square root? Let's just remind ourselves how that would simplify. I'm going to jot down a few notes here on the side and then ultimately erase them. The 16 would factor out, and we get secant squared minus 1. The secant squared minus 1 could be replaced with tan squared. So we have 16 tan squared. And so the square root of 16 tan squared is just 4 tan theta. So utilizing this fact, I'm going to take everything that's in that square root and replace it with 4 tan theta, because, well, that's what we simplified it to be. And so now let me erase this here to get this out of our field of view. And so going back to our expression of interest, actually, hey, there's a lot of stuff canceling here, right? This is not too bad. The 4 downstairs cancels with the 4 upstairs. The tan downstairs cancels with the tan upstairs, right? Because all this bit that was in the dx was like dx over 1. That was all upstairs. One of the secants upstairs cancels with one of the secants downstairs. And actually that 16 that's inside is just a constant multiple in the denominator. So we could factor out a 1/16, and we'll be left with just 1 over secant theta d theta. Hey, that's not that bad, right? I mean, so it looked complicated at first once you wrote it all out, but actually letting all the trig do the talking, boy, there was a lot of simplification. Now, we're sitting here and thinking, oh my gosh, what is the integral of 1 over secant theta? If you did integral of secant theta during trig integrals, you know that that is a beastly thing. But actually, 1 over secant theta is simpler than it needs to be, right? Or, well, 1 over secant theta is more complicated than it needs to be. 1 over secant theta is just cosine, right? Because secant and cosine are reciprocals of one another. And so ultimately, what do we get here? We get 1 over 16 integral cosine theta d theta. And that is beautiful, right? That is, I mean, it's not insulting at this point, but that's at least a nice thing to see because, my goodness, this is straightforward. What function has a derivative of cosine? Just sine. So we have 1/16 sine theta, throw on the plus c because we just computed an indefinite integral, and we're almost done. The only thing that is preventing us from circling this as our answer is the fact that this computation that we have to this point is in terms of theta, whereas our original function was in terms of x. So what we now need to do is figure out what the hell of sine theta is. Now we know sine theta using SOHCAHTOA is opposite over hypotenuse. So I'm going to take a moment and just sort of take the sine theta and replace it with opposite over hypotenuse, knowing that that's what's going to be plugged in for sine theta. But now we got to figure out what is the opposite and what is the hypotenuse in this setting. Where is there even a triangle lurking within this situation? Well, check it out. If we go sort of all the way back to this original substitution, x equals 4 secant theta, something really beautiful happens. Check it out. So what I'm going to do is take a moment and rearrange that. Dividing 4 from both sides, you get x over 4 equals secant theta. Now, this is giving us a ratio associated with secant, which, if you remember from trigonometry, secant is the reciprocal of cosine. So secant is just hypotenuse over adjacent, right? If cosine is adjacent over hypotenuse, its reciprocal is hypotenuse over adjacent. But now, make the connection here. Hypotenuse x, adjacent 4. There's a triangle there. Hypotenuse x, adjacent 4. Using Pythagoras, you can figure out the missing side, and in fact, the missing side is the exact square root that we built our whole logic off of to begin with, because you'd have 4 squared plus something squared equals x squared, which means this side is the square root of x squared minus 16. Check it out. This is the exact same square root from your original expression, and this is not a coincidence. In fact, every time we run through this right triangle computation, we get to this exact same situation. So now, what do we need to do? We need to compute the sine of this angle theta, because once we do that, we've resolved this integral completely. And so to polish this off, 1/16 sine theta, opposite over hypotenuse, is square root x squared minus 16 over x, right? There's our opposite, there's our hypotenuse. And now we've expressed the integral all the way in terms of x. Quite a victory, quite a process. Nothing comes for free whenever it comes to this question of great historical significance, but utilizing our knowledge of SOHCAHTOA, we actually were able to deduce the nature of this antiderivative function in terms of x rather than in terms of theta. So you'll go through many more examples, and it will take time to sort of acclimate to yourself to this process. But I will say, you know, when it comes to even your next test that's on the horizon, like getting this knowledge under your belt will put like 10 or 12 points in your bank going into the test. So it's definitely worth your time to go through this struggle. And it's just a nice exercise mathematically to ultimately leverage trigonometry and to leverage all of the various forms of trigonometry, from identities to right triangles, solving a question that relates to something so historically significant as the birth of calculus itself back in the 1600s. So pretty cool stuff. And well, I've got to stop talking for now. That's enough. I'll see you guys next time.